Question 2. Tennis balls are tested by starting from rest and dropping them vertically from a height of 2.54 meters above a horizontal hard ground. The ball must rebound to a height of 1.35 to 1.47 meters after the collision. The mass of a typical tennis ball filled with nitrogen gas is 0.057 kilograms. Calculate the kinetic energy of the ball just before it hits the ground. So the kinetic energy that it gains is, we know, equal to the gravitational potential energy it's lost, which we can say is m times g times h. So that's 0.057 multiplied by 9.81 multiplied by 2.54, which gives us 1.4 joules. Two significant figures probably because of this, although the question's a bit inconsistent on significant figures. Describe the energy changes that occur during the collision of the ball with the ground. So the kinetic energy of the ball initially we certainly see goes to some strain energy as the ball is squashed on the floor, and then we've got a transfer probably from both of those, I suppose, that goes into the thermal, or perhaps we prefer to call it the internal energy of, well, we've got the gas inside and the ball and the floor. All of those things are going to receive some of that thermal energy and warm back and warm up slightly. But the stuff that doesn't go there, the strain energy, some of it goes back into the kinetic energy of the ball as it rises again. So it's quite a complicated situation on what seems to be fairly simple as we go through it. The table gives values of the volume, pressure and temperature of the nitrogen gas inside the ball before the test, and the values of pressure and volume during the test at the instant the ball is stationary. During the collision, the pressure and temperature of the gas increase while the volume decreases. Using ideas about molecules and momentum, explain why the pressure of the gas increases. So we've got, first of all, the idea that the volume decreases. So the volume decreases. That effectively means the walls are closer and the distance particles, molecules travel between collisions reduces. Collisions reduces. In other words, even without the change in temperature, they hit the wall more often. But then we also have the temperature increases, so the particles travel faster. And again, this causes them to hit the walls harder and more often. It mentions using ideas about molecules and momentum, so it would have probably been good to have in there the idea that when a particle bounces off the wall, we get the particles change momentum and force is rate of change of momentum. That would have sort of completed our description that we had over here. Then we get to see the molar mass of nitrogen is 0.028. R is 8.31. Hopefully we're fairly familiar with that by now. K is 1.38 times 10 to the minus 23. The Avogadro constant is 6.0. If we're just doing it to two significant figures, times 10 to the 23. Calculate the number of moles of nitrogen inside the ball. So we can use PV is equal to nRT. N is PV over RT, which here is 180 times 10 to the 3 for the pressure, multiplied by 1.08 times 10 to the minus 4 for the volume, divided by 8.3. Everything else is two significant figures, so there's no great need to carry the extra significant figure. The temperature is 293, isn't it, from the table? So that gives us a value of 8.0 times 10 to the minus 3 moles. The number of molecules of nitrogen inside the ball, so we just do the number of moles times Avogadro's number. So 8.0 times 10 to the minus 3 multiplied by 6 times 10 to the 23, which gives an answer of 4.8 times 10 to the 21. 3, the total kinetic energy of the gas molecules before the ball is dropped. So we have to be careful here because we've got the total. So we want N times half M, and then because we know we're dealing with the molecules here, C squared bar, so the average, the mean square speed. That's what I'm trying to say, the mean square speed. Well, this should be equal to N times 3 over 2 kT, because 3 over 2 kT is equal to half mc squared, and we know the values of all of these. So this is 4.8 times 10 to the 21 multiplied by 3 over 2 multiplied by 1.38 times 10 to the minus 23 multiplied by the temperature 293, which is 29 joules. The temperature of the gas inside the ball at the instant that it's stationary. So we're back to ideal gas law. PV is nRT. So T is equal to PV over nR. We've got new values for pressure and volume. So the pressure's gone up to 200 times 10 to the 3. The volume is decreased to 1.00 times 10 to the minus 4. The number of moles, not particles, isn't it? Number of moles, 8 times 10 to the minus 3, multiplied by the gas constant, which we can just have as 8.3, so that should say 8.0. So when we come to calculate this, we get a new temperature of 300 Kelvin. If I write it to two significant figures, 301 if you were still going to 3, but I think we should still really be at two significant figures. And then if we work out the kinetic energy of the gas molecules now, so same thing as we did before, this is going to be equal to N times 3 over 2 kT. So N hasn't changed, 4.8 times 10 to the 21 multiplied by 1.38 times 10 to the minus 23. Don't forget the factor of 3 over 2, multiplied by the temperature. So that's 300, which comes out as 30 joules. And then D says, compare the values you obtained in C3 and C5 with the kinetic energy of the whole ball in question A. And so we've got, let's write these down so that we can see them. The value in C, so that was the total kinetic energy before it was dropped of the particles, 29 joules. After it was dropped, we noticed it increased to 30 joules, and the kinetic energy of the whole ball was 1.4 joules. And so I suppose we could first of all notice that the internal energy of the gas is quite a lot bigger than the kinetic energy of the ball to start off with, if we're comparing these. And then the second idea is that some of the 1.4 joules of kinetic energy is transferred to internal energy, which we can see increases from 29 to 30 joules, which is why there's less kinetic energy afterwards and the ball bounces lower.